can see it.
Okay, good. All right, go back. So first up, we need to know what type of forces we're going to deal with. We are going to be dealing with either compression or tension. Okay, so if you're going to build a bridge and you have beams that are going to have to hold something, they will either be getting compressed or having tension to it or being pulled. So either they're going to be getting pushed in and they have to handle that compression force, or they're going to be pulled and that's going to be tension, right? So, I mean, it's pretty easy. If I had this meter stick, that's basically the two things that this meter stick could do. I could push it, and obviously you see, oh, that must be compression because it's pushing out. Pulling it, right? So there's tension. So if something's being held up by a beam, what kind of force is that going to be? Tension, right? If I'm holding something up, there's going to be tension. If I have something on top of this beam, it's going to be compression. So those are the types of forces that we need to know how to deal with. And what engineers are going to have to do is when they're building, when they're using certain beams, they're going to have to say, all right, this beam can handle so much tension. This beam can handle so much compression. Okay? All right. A truss. A truss is...
Could you please go back just for just one word? Like,
is that enough?
No, like next slide. Yeah. Stretched. Okay, thank you.
All right. So a truss is basically going to be, so it's a bunch of different beams that create the structure, right? And those beams, usually you're going to see this triangle type of shape to create a truss. All right, let's look. If we have those beams just like that, it might be able to handle strength in one direction. However, apply force in the wrong direction, and it's not going to hold up. That would not be helpful, would it? So we add a triangle going across the middle, and now it's going to be able to handle forces in all directions. Okay? So that's why we're using triangles. All right. Do I need to go slower? I can slow down. I mean, I don't think you really need to go word for word with this stuff. Especially because you have it all, you can download all of it on PLTW, right? So you don't need to copy word for word. You just need to get the gist of it so that you can go back. And you can always go back to PLTW, mypltw.org, to get the word for word stuff. And that's going to be important because we got 29 slides. So if I go back and forth for Manroop again, we're all going to throw something heavy at him virtually. Okay.
I just have a quick question.
Yes. What's up, Manroop?
So the square, I mean the rectangle that doesn't have a like that diagonal line, that's good, but the one that doesn't have it, that's not a good thing.
Yeah, because there's nothing that keeps it solid. Like these are bolts, right? So applying a force, this won't keep its shape, which is not good.
Okay.
So that diagonal makes sure that it keeps that shape the whole time.
Okay.
Okay. We already learned this, but here's going to be our laziest way to draw a pin in a roller. All right. So we already talked about this. It depends. So a pin, we know, has two reactionary forces, vertical and horizontal. A roller, and this picture over here is showing, I don't know if you can see my cursor if I do that, but okay. This is just showing like this is the wall. So you could use a pin. You don't just, it's not just on the ground. You could also have a wall and put a pin or a roller against a wall, right? So there's a pin and pins on both either a wall or on the ground. Here's a roller, and we know that a roller only does one direction, either vertical or horizontal. If it's on the ground, it's going to be vertical forces it fights against, which would be, and I'm going to write that on here. I won't be able to write it on for everybody to see it. Okay, well, let me see if I can do this. Maybe. Can I do it? Will it work? Let me see if this works here. For some reason, I think it doesn't, but let me see. On Zoom, it doesn't work for me anyways. It'll probably pop up in 2 seconds. Oh well. Try one more time. Nope. All right. If you wanted to label these forces, think about what the force would be. So for this pin, we would have reactionary force. So you would have R. And then we would say if it's going to be in the vertical or the horizontal. So we would have reactionary force Y for vertical, X for horizontal. Okay? So we would have to label forces for a pin as R, Rx and Ry. And we'd also be labeling it like, whatever that location was. Is this point A, point B? So you would say RAY if it was point A on a truss and talking about the vertical forces it's fighting against. Okay? Where here there's only going to be, it could be Y if it's a roller sitting on the ground. It could be X if the roller is sitting against a wall. Okay? All right. Next. Maybe. Oh, now. Look at that. Oh, there we go. RAY. Great. That's not so helpful anymore. Do I want to keep it? I really do not want to keep that. I'll discard it. And now I got to reload it. Okay. I need to reshare. Sorry, I got closed. Okay. All right. Moving along. All right. Here are assumptions we can make anytime we're doing trusses. So we can always assume that the members are all perfectly straight. All loads are going to be applied to the joints. So we're going to be looking every time we do forces, we're going to look at the joints, because the joints, wherever two bolts are going to be, or a bolt's going to be, that's where it would take the most amount of, that would be where the weakest point could be. Okay. So we will assume that the members are much stronger and the joints are going to be taking on all the loads. Okay. All joints are pin and frictionless. You don't need to worry about that so much. This is a big assumption, but what we're going to do when we do our calculations is we're going to assume every beam that you see, every member doesn't have weight to it, which is wrong, right? It's dead wrong. But what we're compared to how it's going to handle a load, we're just going to pretend that the beam itself, so no matter how long a beam is going to be, we don't have to add the weight of the beams to our calculations. Okay, so you won't have to worry about the mass of a beam. You'll just worry about the load that's sitting on it. Okay. Actually, come to think about it, all loads applied to the joints. That means really that we're gonna, like, if we draw a truss. If we put a box and say there's 500 pounds of force or 5,000 pounds of force, we'll put it at a joint spot, I believe. Okay. And members can only experience tension or compression forces. All right. And we won't worry about that right now. All right, we did this already, right? We did this last class. Hopefully you remember this from last class, if something's statically determinate. So we'd have to do that calculation, 2J is equal to M plus R. You did that last class when we were dealing with moments, and we talked about that. Do we all remember that? Hopefully so. All right. So let's practice it again. If we have a statically, is this going to be statically determinate? Well, we're going to have to go through we would have to count the joints, the members, and the reactionary forces. So what do we got? We got, let's count the joints. We got A, B, C, and D. So there are 4 joints. Okay, so far we have our J, 2J, we have 8. Now, what about our members? We have 1, so I have AB, so there's 1. BC, that's 2. CD, that's 3. Okay, DA, that's 4. I have BD, that's 5. So I have 5 members. Do I need to go back through that again? I really want to try to paint again because it would be not much easier if it did. Laser pointer, that's interesting. And so we got AB. Can you guys see this drawing now on Zoom? Okay. So we got 1 AB, we have BC, that's 2. CD, that's 3. 4 AD or DA, and 5 is going to be BD. So far we have 2. Oh my God, I can't write like that. 2 times 4. Can you see that? Okay. So we have 2 times 4. Don't judge me on that 2 or really on that 4 either. We have a 5 for the members. And what about our reactionary forces? How many reactionary forces do we have? Don't say it. Put it in the chat. I want to see who's awake. Chat me up. How many? Go ahead and hit enter. How many reactionary forces are there? And Roop, you are lazy. You are very lazy. All right, so we have some people answering questions. And some people just thinking they'll say, oh, what he said or she said. All right, but very good. So we should have we have reactionary forces. We have 1, 2. And now that I can write, how would I write that? I would write as RAY, right? And oops. RAX. And then we have RCY and RCX. Now that arrow, those arrow directions might not be pointing in the right direction, but that's okay. All right, so we have 2 plus 4 is that, or 2 times 4, is that equal to 5 plus 4? And we all know that that is not correct, right? So 8 does not equal 9. So it is not statically determinate. So there you go. All right. Now, if we switch this one, and now we have the same thing, we're going to have 2 times J. We still have the same number of joints. So we got 2 times 4 members. We still have 5. But in this case, we have 1, 2, and 3. Well, now it's going to be statically determined. Right? Right. Okay. So there's the calculations there to give it to you. Each side of Main Street Bridge in Brockport, New York, 19 joints, 35 members, and 3 reactionary forces. It's got a pin and a roller. Now, most of the time, again, why is it that we need a roller? Why do you think we want a roller in some cases?
The bridge may expand or contract.
Excellent. Yes, sir. Thank you, Pranav. Yeah, the bridge might expand. So we obviously need to have at least 1 pin because if they're both on rollers, it would roll to the side and then into the water. So we do need to have 1 pin. Okay, but we usually need to have one kind of roller because of expansion. We need to deal with expansion here. Okay, so there you go. So there is a real life example of making sure a bridge is statically determinate. All right, so we did this already, sums of the moments, right? So the idea is going to be this: when we start doing these trusses, we are going to have to do, your first thing is you want to double check and make sure it's statically determinate. I mean, that's kind of an important thing to do, but most of the time when I give you a truss, it will be statically determined. Okay, the next step is then you need to do the sum of the moments. Okay, because the sum of the moments are going to help you figure out the forces of the pins and rollers. All right, so you'll always want to start with the sum of the moments. And so that was the first thing. Then we go to the sums of the forces in the x direction. Okay, then you can do sum of the forces of the y direction. And that's going to be of the whole truss. Okay, now, for all of these, sum of the moments, sum of the forces in the x, and sum of the forces in the y. Unless you want to have a bridge that won't last very long, all of those sums have to be what? They all have to add up to 0. So you will write sum of the moments. Then you're going to have, RA or moment at A, moment at C. Add them together. They have to equal 0. Okay? And then underneath it, you would put in the equations for each one and how those go. All right? So here is how that would look for the first one. All right? So if we have a rotation, we have sum of the moments for, so we have the sum of moments at the A. And you always want to start with a pin. Okay? This got ugly really quickly. I thought it was going to be better than I started. Okay, so we want to find, so we're going to use the moments to find RCY. All right, so looking at the top. That means we want to have our pivot point at A. All right, so we're going to do our pivot point at A here. So think about what forces are going to be acting in each direction. So don't get too worked up with what you see down below you. So I have this point here, right? Here's my pivot point right there. I'll do it in color. Here's my pivot point. I have two moments that are fighting against each other. Okay? We have the moment from the 500 pounds at point D that wants to turn the bridge clockwise. Okay, so let's start doing the sum of the moments. Let's try listing it. Sum of the moments, we're going to say at A. All right. We have the moment at D. Okay. And that wants to cause it to go clockwise. We'll worry about positive and negatives in a second. We'll go back and make sure they're positive and negative, right? All right, what about the other thing? So then if D is causing this thing to rotate down, that means C has to be pushing back up because the bridge is not spinning around in a circle. Okay, so the only other moment acting at to try to cause a rotation at point A is going to be the moment at C. So far, so good. All right, now we know this is 0. We know that the sums are going to add up to 0, so I can just put a 0 there. Now, moments are going to be force times distance. Remember, it was force times perpendicular distance. They have to be perpendicular. So let's think about what we would put if I wanted to substitute in the equation for force times distance for moment of D. I would write the force at D times the distance at D. Does that make sense so far? Hopefully so. Okay. So and then I'm going to substitute in. Oh, and I forgot to do the positive negative. Real quick. Let me take a step back. I won't erase anything. D is causing it to go clockwise. If this was a piece of paper and not on the screen, my thumb would be going down. Is that a positive or negative moment? Negative. So this is really going to be a negative right here, right? And a negative right there. All right. Force at C, or the moment at C, is going to be curling up. It's a positive moment. So that one's good. Okay, now let's substitute in the equations for moments at C. We have force at C, which we will rewrite in a second, okay, times the distance at C. Now, we are naming the forces on pins and rollers reactionary forces, okay? Because there's a reactionary force there, the force that we need to use is going to be the force pushing up, which is the Y. It's reactionary, and it's at point C. So that's why we can change that force of C. No, it's not going to erase. Right over it. As RCY. Okay. So let me take a step back and explain it. The numbers in the calculation are off the side already, so I don't need to I can talk through it, but I'm not going to write it down. Okay. So what did we just do? We picked A as our pivot point because it had a pin. And you want to pick a pin when you start these calculations. What we did first is we figured out that if A is where it's pivoting, there are two things that are fighting, and they're fighting against each other. We have the moment at point D. So a moment of whatever the force is at D pushing down and trying to make the truss rotate clockwise. Then we have the moment from point C pushing back up and a force of pushing up, the RCY, pushing up to try to cause it to rotate counterclockwise. Okay? And they obviously have to add up to 0 because they're not, the bridge isn't spinning. The truss is not spinning here. Okay?
Mr. Spirik, I have a question. Why didn't you add RAY into the equation for the summation of?
Because RAY, so the reason I chose A as the point was because it had a pin. So it's rotating at A, which means any force being applied at A is on the pivot point and would not cause a rotation.
Okay.
Okay? So that's why when you start, that's an important step, is to say, all right, which one's my pin? And most of the times you have one pin, one roller. You want to pick a pin to start your moments. Okay? Because if you did moments at A, let's say you said, oh, I got RAY. Well, the distance from A is 0. Does that make sense? So any force times 0 is 0. So the moment would be 0 anyways. All right. Okay. So then what we did, here's the calculations or the numbers they start putting in. So the force at D, we don't, we do know it's going to be 500. The distances have to be from the pivot point. So the distance here is the distance there, which is 3. The force is 500. And we know that it's a negative because it's a negative moment. All right. The RCY, we don't know yet. We need to find out what that force is going to be. So we just leave it as RCY. Okay. And then again, the distance from the pivot point will be 3 plus 7 for C. So we have 10. All righty. Okay. So there's a big calculation, and I have that is equal to 0. From that point, what you're going to be able to do is algebra to solve for RCY, right? And it shows the algebra down below, but basically negative 500 times 3 is going to be negative 1500. You bring it to the other side, so you have, that's how you get 1500 is equal to 10 times RCY. Divide both sides by 10, and you get RCY is equal to 150, which is what they have down below. Okay? All right. I understand that was not fun. And I understand that that is not something that comes natural. But the key is this. I want everyone to recognize the steps. Okay, the steps are, I picked my pivot point, and I picked the pivot point to be where there's a pin. Then I looked at what forces are causing something to rotate in either direction. And I saw that I had D wanting to make this rotate clockwise around A, okay? And C would have to fight against it, so it's causing it to go counterclockwise, okay? So that's what I listed up top. That's why I listed that at the top, right? Then all I did underneath was substitute the equation for moments. Moment is force times distance. So for D, it was force times distance at the D point, okay? For C, it was force times distance, but the force that we're going to use is reactionary force because for RCY. So we changed force C to RCY, okay? And then we plugged in numbers. So the key is just keep it simple at first. Here's my sum of my moments are going to be 0. And what moments are there? This moment plus that moment. Then take another step. Let me put in the equations underneath. Then take another step, put the numbers underneath. Just go slow and do the step by step. Okay? All right. So that's how you'd figure out RCY. So we just figured out, write in your notes somewhere, that we figured out that RCY was 150. So we know that at point C, the roller is going to be pushing up and helping to hold up this bridge with 150 pounds. Okay? Now let's think about the forces. If we talk about the sum of the forces in the Y, all right? If we have 500 pounds of force that's pulling down, and we don't want this truss to fall through the earth, and we know that there's 150 pounds of force here, well, then the other spot that's helping to push up has to push up with the rest so that we can cancel it out. So if I did sum of the force, I know it's over there, but I'm going to write it again. So we're looking at just the overall truss, the sum of the forces total, okay, in the Y direction. We have 500 pushing down. Okay, I'm going to make it negative because it's going to go down. We have 150 already pushing up, which was RCY. Okay, and then we got to figure out what RAY is. Well, remember that the sums of the forces have to add up to 0 because it's not going to be going up or down. So then we could just do our algebra and solve for how much force does this have to push up with. All right? So 150 plus or 500, negative 500, positive 150 would get me, so I still got my 0 underneath. I got negative 350 plus RAY equal to 0. And you can do the algebra and then figure out that RAY must be pushing back up with 300 pounds, 350 pounds. So that's why you got this value down here. Okay? That's a lot so far. The next step, which is going to be trickier, is then you go into each point. You go into point A and say, what's going on point A? You go into point B, and that's going to be a lot of stuff. Where do I want to? All right. Well, I'm going to move along from there. Okay. Now it talks about the forces in the X. So the sum of the forces in the X, if it's not going to be going one way or another, it's not sliding horizontally, it must mean that the forces add up to 0. So you do the same thing in the X direction. But there's only one force acting in the X direction that you see there. Do you see what's the force? I'm going to let you type this in. What is the force you see in the X direction? Nobody, huh? Yeah, there we go. Ooh, I like it. For now, that was a good way to write it. I was going to say, don't try to do subscript. Good. So the only force in the X direction on this truss is RAX, right? So RAX must have 0 newtons of force because it's not fighting against anything else. So if the sum of the forces are 0, and RAX is the only force to list, right? So understand what it did. It just listed the sums of the forces equal to 0, and then you list the forces underneath. The only force is RAX, so that means RAX will have 0 pounds of force on it. So RAX, that joint could be very, very weak because it's not going to have any forces whatsoever to apply to it. All right. There you go. All right, now looking at joints, you need to use sine cosine if something's at an angle. Okay. Assume all forces are tension. Okay. So when you do the calculation of, so point B, look at point B, what they're trying to show you. There's point B up there. Everybody look at point B, right? What you would do is you would go through all the letters and try to solve for all forces that are acting on it. Okay? So at point B, they draw a picture that looks like that. Okay, and they say, all right, well, all the forces are, what forces are acting on? You're going to have, this force here, this force there, all these forces. And what they want you to do is always assume that the force is positive, and that means it's tension. So if forces are going away from B, that's positive. If forces start pushing in, so if you end up finding that the force here is pushing in, that would be negative. Okay? But we are going to assume that all of them are going to be positive forces. If you get a negative force, that means there's compression going in on that joint. Okay? Or on the member. So the beam itself would have compression on it. Not so much the joint. All right. And then once you get all the forces done, you update your free body diagram and redraw it. Okay. The dimensions you will use to calculate angles. And that'll help calculate forces. So the dimensions you see, when you see numbers, so if we have a 3 and a 4, that will help us figure out the angle for this one. All right, let's do a quick calculation for everybody. I want everybody, don't blurt it out. I want everyone to remember their notes from angles, from vectors, and I want you to tell me what is the angle of 1 going to be, and what is the angle of 2 going to be. Don't blurt it out. Don't put it in the chat. I want you to calculate it, and I'll tell you when to put it in the chat. Go ahead and do it. Put it in your calculator. Get it? That's not a, no, I want you, I don't think you're, I want you to get your sides, do SOHCAHTOA and get this. Just, you're saying because that's a square angle? Yeah. Whoop. No, wait. It can't be a square because this is 3 and that's 4. Hopefully you have that little cheat sheet from SOHCAHTOA we talked about. I don't see 45 degrees, but we'll look and see. All right, let me give you a hint. Anytime you're solving for angles in this class, it will be that you have a horizontal and vertical. Okay, and in this case, let's do 1 first. So theta 1 is going to be inverse tangent. Remember, we use inverse tangent because of opposites and adjacents. Hi, Mr. Linton. So we have our vertical, or it's always going to be inverse tangent of the vertical piece over the horizontal piece. Okay, so it's opposite over adjacent, but in physics it will be vertical over horizontal, or in engineering, sorry, it'd always be that we have the angle on the connect to the horizontal. Okay, so you can say that's vertical, and this is the horizontal. Okay, so to get that angle, it's going to be inverse tangent of 4 divided by 3. So second tan. 4 divided by 3. Get, yep. All right, type it in. Hit enter. Oh, Brandon, you're on the ball. You did both of them. All right, so the other one was going to be second tan of 4 divided by 7. 29. Good. All right, so the first one should be 53. It's 53.1 or something like that. Close enough for government work. And 53 point something. I don't know, whatever you guys got. 4 divided by 3. 53.1. And then we do the same thing over here. So we do inverse tangent. Again, the vertical is 4, but now the horizontal is 7. 4 divided by 7. That's for theta 2. And we get that to be 3 to 7, 29.7 degrees. Okay. Good, that's better. Okay. All right. I told you this is where we hit the fan. So then once you do that, I already showed this part. We got the angles. Boom, boom. Yep. Do the other one. Boom, boom, boom. 29.7. Okay. So then you would use those forces. And we would be breaking up. So like for every point, so again, it says in here, every member is assumed to be in tension. A positive answer gives you that tension. A negative answer gives you compression. Okay. So when you're doing your forces, you're going to look at these forces and say, all right, well, you know, if this value here, so like if RAY is going to be applying a certain amount of force up, then something about B, or I'm sorry, something about that piece of A has to be fighting against it. Okay. And then you just go to each part and say, all right, what are all the vertical things going on at A? What are all the vertical forces at point A? What are all the horizontal forces at point A? They all have to add up to 0. And then you start solving piece by piece for all the forces. All righty. When you name it, so choose a joint that has the least number of unknowns. So reaction forces are both good places because you just calculated it. So we already calculated RCY first. Then we calculated RAY. Okay. Well, RCY is going to have 2 arrows to deal with on top of the, or I'll say again, point C has 2 arrows that we have to still solve for. Okay. Point A has 2 arrows as well. So I guess we could go either one with either one of those. All right. When we name something, if we need to know about the forces, we'll talk about AD would be the force of that member. AB would be the force of that member. Okay. And so on and so forth. So here I'm going to show you, we're just going to go through, I'm not going to have you do all the joints. But let's just look at what happens when you break this into pieces. So if I want to know the sum of the forces in the, at point A, okay, then we need to figure that out. So what's going on at point A? Let's do the sum of the forces in the Y. All right, so what do we got? So here we go. We write down sum of the forces in the Y direction. What do we have so far? We have 350, and that's going up. Okay. I'm going to write my 350. Or actually, I'm not. I'm going to write in terms of letters first. So I have 350. That was my RAY. Okay. Now, what else? I also have a piece of AB that's going vertical. So the force at the Y or at A in the Y direction. Okay? And those add up to 0. All right, now, let's take it a step further. If we have this, let's rewrite this triangle action. I got AB going like that. And I have a piece horizontal and a piece vertical. Here's my angle. We already know this is 53. This piece will be AB sine theta. And this piece will be AB cosine theta. And specifically, it would be AB sine 53 and AB cosine 53. All right. So let's plug in what we got. So we have RAY is 350 plus AB sine 53. Well, that's really ugly. Is equal to 0. Okay. I want you to do the algebra for that. I want you to tell me what is AB going to be equal to. Go ahead. You can tell me privately if you get it, or you can just wait and we'll go over and check our answer. All right. I want everybody to type in the chat, and I'll tell you when to hit enter. Type in your answer. Do your algebra. Hopefully you did your algebra. Solve for AB. Ready? I didn't say yet, Munib. All right, go ahead, hit enter. Go.
Oh, I did it privately.
I saw. I was joking. Yeah, actually, you did it the right way. I like it that way. That way, that was good. Okay, we got 2 people answering so far. 3. We got 2 right, 1 wrong. All right, so let's do the algebra. That's all we got. 4 people answered it. Boom. All right, so here we go. Let's do the algebra for it. I got that. So I'm going to bring the 350 over. So I have AB sine 53 is equal to a negative 350. Now I'm going to, this is multiplication here. I'm not going to do inverse sine because I'm not solving for the angle. The whole thing goes over. I'm just going to divide both sides by sine of 53. So I have AB is equal to negative 350 divided by sine of 53. And I get negative 438. All right. So because you see a negative answer, that means the force is really going to be compressing on the joint. Okay, that's going to be compression instead of tension. Okay? All right, ladies and gentlemen. Let me look at where that lecture is way too long, and there's more to it, but I don't want to do more to it right now. There's all the calculations without me. So you can go through the rest of these and kind of go step by step through the calculations. All right. So doing the sum of the forces in the X. Let me look at the assignment, see what else we'll be able to do for it. So there are a number of steps you can do. What we just did, okay, these are just the equations. Some of them moments, some of the forces in the X, some of the forces in the Y, or some of the in the Y and then the X, whatever you want to do. Okay. Then you can go through and start looking at the pieces. So what I want you to do is you can start to draw out these pieces for the rest of the class. You can work your way through moments and solve for RCY. Why don't we get to RCY at least on your own? Okay. And then we will work on the rest of the notes later, but you have enough so that you can get, if you look at this, you can work to get at least RCY and get that, what the force will be at point C, pushing back up so it won't rotate. All righty? All right, I'm sending you away.